going to wind up happening is I just pushed the schedule back by one class. I think the only exception to that is the final project. Because I gave you to the end of the semester anyway to do it. But I won't go into it, cover eigenvalues. Today we're going to look at the kernel and the range of a transformation. So consider a linear transformation L from V into W. Right, the range is, of course, all the output values. So the range of L is the set of all L of V such that V is in the vector space V. The kernel of L is the set of all V in capital V such that L of V gives you the W0 vector.
Can you restate what a kernel is? That's like in words.
It's the set of all vectors that go to the zero vector in your output.
Okay.
What was range in words again?
It's just the set of all your outputs. Or the set of all images. These are subspaces. So the kernel of L is a subspace of V, your domain, and the range of L is a subspace of your codomain, W. Well, not that long ago, we studied two special subspaces of matrices, right? The null space and the column space. If you consider a transformation from Rn to Rn defined by A times X, then the kernel of L is the null space of A, and the range of L is the column space of A. next time, we're going to learn how we can essentially write any linear transformation in this form, A times X. A would then be called the matrix of the transformation. So that makes this even more relatable, right? If A is your matrix of transformation, then kernel is the null space of your matrix, and range is the column space of your matrix. So linear transformation from V to W, nullity of L is simply the dimension of the kernel. Rank of L is the dimension of its range. We had a rank nullity theorem, right? For matrices. We have one for transformations. Assuming that the dimension of your domain is finite. If the dimension of the domain is finite, and it's n, then the rank of L plus the nullity of L is equal to n. Right, so the rank of your transformation plus the nullity of your transformation is the dimension of your domain.
Can you repeat that? I'm sorry.
Rank of the transformation plus nullity of the transformation is the dimension of the domain, as long as the domain is finite dimensional. One-to-one and one-to. Think to functions. What does it mean if a function is one-to-one?
For every input, there's only one output.
Yes. Right, each input maps to one and only one. So each element of the domain maps to one and only one element of the codomain. What does it mean for a function to be onto? What do you mean? Well, I mean, we talk about function as it goes onto something, but what does that actually mean in terms of functions? that would not even be a function. Remember, functions, each output has only one input. But that's the same as you have a single output that has multiple inputs, which isn't a function. Wait, no. No. Yes, function is what? Input can only go to one output. Can't map to multiple. Right, yeah, you can't have two go to two different outputs, right? So no. That would definitely not be 1-to-1 though, right? If you had one output having multiple inputs. Function is onto when the entire codomain is covered. Right? Every element in the codomain has an input that maps to it. More succinctly, function is onto when the range of the function equals the entire codomain.
Is that surjection?
That's also called surjection, yes. Onto and surjection, same thing. 1-to-1 and injection, same thing. All right, so x squared, if you go from the reals to the reals, not onto it. Because you don't get any of the negatives. You can make it onto by saying that your codomain is the non-negative reals. Then it's onto. Right? Every non-negative real gets mapped to. Still not 1-to-1 though. Well, we also have 1-to-1 and onto transformations. We say that T is 1-to-1 when the kernel is zero-dimensional, meaning that the only element in the kernel is the zero vector of the right, and W is finite dimensional. L would be onto if and only if the rank of L is the dimension of W. Right. Other notation you may hear, 1-to-1 you may hear as an injection. Right, so T is injective, or is an injection if it's 1-to-1, so that's satisfied, and surjective is onto. It's a surjection if it's onto. If it's both, it's called a bijection or bijective. Bijective transformations are pretty important. Transformation has both 1-to-1 and onto is called an isomorphism. Moreover, if V and W have an isomorphism, then we say that V and W are isomorphic to each other. Which is very important. Two vector spaces that are isomorphic behave the same way. So if a property is true in one, it's true in the other. As a result of this, Finite dimensional vector spaces VW are isomorphic if and only if they have the same dimension. Any vector spaces that have the same dimension are automatically isomorphic, which means they behave the same. Typically, then, what we'll do is if we know the dimension of a vector space, say P3, what's its dimension? What's the dimension of P3? 4. We treat it like R4. Oh, but remember when we wrote the coordinates? It wound up being a vector, right? So we essentially will just convert everything to a vector. Which means now we're given, it's not going to happen in this course, but let's say it's a more advanced linear algebra course, you're given a very abstract vector space that's kind of difficult to work in. But you know its dimension is n. Just work in Rn instead. And you want to prove a property about this abstract vector space, just prove it holds in Rn and you're done. If you can prove they're isomorphic, which you can if you know the dimensions are the same. Looking at a transformation from R4 into R3, right? That way, find a basis for the range and basis for the kernel, and determine their dimension. Write that down. Need to rant. Need to get this off my chest. You know, Windows 11 took away a nice feature. Doesn't let you move the taskbar. Taskbar is fixed at the bottom, which is really annoying. Means I have to actually have the taskbar auto hide, so I stop accidentally clicking on it when I'm writing. So annoying. Yeah, Windows peaked at XP. It's been downhill since XP. But even Windows 10 allowed you to do the taskbar. Why did they took that feature away? So annoying. Hopefully they bring it back in Windows 12. Because they got a lot of complaints about it.
So you can't just update the latest software to bring that back?
You expect Microsoft to add a feature they already took away without a brand new operating system? Where are they going to get their money from? They're going to force everyone who wants that feature back to buy Windows 12. And I guarantee you that'll probably be the only feature change in Windows 12 and they're charging like $800 for it. They used to offer free updates. I guarantee you they're not going to do that. I guarantee Windows 11 and Windows 12 will not be free. They're going to charge you for it. I can guarantee it. With one feature change. And it'll be a feature that everyone wants, so I don't have to pay for it.
I think for newer computers, they're replacing like the Windows key with the
it's not
Microsoft Copilot key. Yeah.
Are they, or No, they're replacing, I think they're replacing, the right control key with the Copilot. Because mine is like that, has the Windows key, no longer has a
Oh,
right
they've
control
already
key.
done it. Oh, shoot.
The right control key is now the Copilot, not the, and so you lost the control key. Wouldn't surprise me if they eventually get rid of the Windows key. And probably charge you like $100 for a keyboard with it, $100.
That's why people are still trying to make Windows XP work. The only problem is, you connect it to the internet and it just gets flooded with viruses.
Because there's no more security updates for it. That's why I said they peaked with XP. The biggest flop was 7. Windows 7 is a huge flop. Why do you think they rushed out 8? Because of how much of a flop 7 was. They came out with 7 to make it like compatible with the Xbox. And like nobody wanted it. So they got flooded with complaints, so they literally rushed out 8. I think it was also compatible with the Windows Phone, that also only lasted for a little bit.
Oh, God.
Windows Phone is dead.
That's
What the
sad.
hell is it?
It was Microsoft's phone. The phone was actually Windows operating system for mobile.
The Android or?
No, Android was not, no.
The
Android is
Windows,
its own operating phone, to Google.
the Windows phone looks terrible.
It was terrible.
Microsoft even had run iPod with Zoom, which lasted for like 2 months.
Again, it was also supposed to work with Windows 7, but Windows 7 was such a huge flop. They were like, nope.
That's because XP was just fine.
They put up so hard.
Well,
I would imagine.
ME was before Windows 7. It was XP then ME.
I thought it was like me then XP.
Me came after XP.
And then, I thought it was like XP Vista and then 7.
Oh, maybe Vista was the one that came after XP.
I remember people really didn't like Vista.
Maybe that's right. Yeah, I think you're right. Me, XP, and then Vista. Vista was awful.
They're going to be continuing the Windows phone in 2025.
I was wondering.
After a brief hiatus, according to.
A brief hiatus? Yeah, several years is not brief.
I'm reading there.
I think the Windows Phone only lasted a year. That's awful.
Clearly, they did a good job, because they don't even know what it is.
Microsoft's definitely gone down. I remember their Xbox One announcement. You can't share games! And they were like excited about it.
And then PS.
And they got booed.
And it's
And then the PS4, the first thing was, you can share games.
They're like
Standing ovation.
It's crazy. They're like, yeah, you can do that?
My Xbox 360 isn't working anymore, I don't know what's wrong with it.
It's because it's 360, so they discontinued it.
When did they discontinue it?
I can't go online.
They discontinued it when the Series X was announced.
So I'd say like 2014, 15, somewhere around
I
there.
still play my 360.
No, it was, because they were still updating it, even with Xbox One.
Yeah, I
It was with Series X that they decided.
Because I remember
they wanted 360.
GTA 5 came out for the 360. Or there was some game, but it was like on numerous discs because they had to like backport it. Something crazy like
I
that.
wanted to play Skyrim, and it was somewhat working, but the moment the controller vibrated, it just shut down.
It's out of expected.
We're going to first find the kernel. So remember the kernel.
My Skyrim copy is still in the thing. I can't get it out.
Boy, you can. You just have to take the entire thing apart.
I know that.
Which why you're finding the consoles. Get the PC.
I got it a long time ago, and I was pretty nostalgic. Plus, I haven't finished the
I can't play them on it.
I don't have PC money.
Huh?
I don't have PC money. That's a whole different level of money I need to invest in.
I prefer.
Yeah, but the mods make it worth it. Trust me, the mods make it worth it. I started modding and I can't go back on.
I guess it depends on what you're playing.
Thankfully, at this point, Skyrim is so old, it can run on probably anything nowadays.
Yeah, I played, I just didn't actually.
I still need to get my
But-
monkey out of the console. It's stuck in there. I haven't finished the official quest. I was supposed to doing it. I should some side quests.
You can get like, even after 14 years.
Remember, kernel is the set of all vectors that map to the zero vector. Right, which means we need to solve this. What does that look like? What is it? More specifically, what kind of equations are they? Linear. System of linear equations. How do we solve a system of linear equations? Oh, look, we're going back to RREF. That's actually a system of homogeneous linear equation, right? That's a homogeneous system, which makes the matrix, the row reduction, even easier because we ignore the augmented part. We just have the coefficient. Can't recall. I don't think we did row reduction with transformations, did we? So it's been a while since we looked at row reduction. We're back. Row reduce that. Just verify. But that's what you get. The kernel set of four vectors. Remember, the kernel is going to be a subset of your domain. Right? So it's a subspace of your domain. So it has to be four vectors. Just interpret this. And x1 plus, well, I guess it's x1, right? X plus 2z minus t equals 0. So what does x equal? Negative 2z plus t, which I'm replacing with r and s. Just so that I don't want to use the independent variables. R and s are going to be random numbers. That's your kernel. It's the set of all four vectors that look like that. Remember when we were finding the kernel of, not the kernel, I'm sorry, the null space of your matrix? And we want to find a basis. Do you remember how we did that? Your row is a linear combination of R and S of your free variables. Go back to your notes. Because I'm not going to redo it here. I'm not going to redo that step by step. What we're going to do, I'm going to call basis for the kernel like a kind of fancy looking K. Look in your kernel. Look at the coefficients for R. What are they?
-2, -1, 1, 0.
Is your first vector in the basis. Why is my touch screen not working? So is that my touch screen or just, okay, so it is just PowerPoint, so if I restart PowerPoint.
New brand new force, and when I walk by a tower, they started attacking every smartphone. I don't know if that was a bug.
Oh, going to do the same thing now for your second or your second free variable S. Coefficients 1, 2, 0, 1. There's your second vector. And there's your basis for the kernel. Right, it's obvious that they span because it's a linear combination of R and S. Right, so every vector can be written as a linear combination of these two vectors. And it shouldn't be difficult to show that that's also automatically linearly independent. Because it's a linear combination of only your three variables. So what is, it's not asking for it, but I'm going to do it anyway. Oh, it did ask, right? It asked for the dimension, which is, of course, the nullity of F, which is the dimension of the kernel. What is it?
2.
How many free variables were there?
4.
2, right? 2 free variables. Oh. I wonder if that's always true. I'll leave you to prove it. We should know what the dimension of the range is going to be at this point. What should the dimension of the range be?
2.
2. Why?
Because the range will be bigger than
What's the dimension of our input?
4.
Dimension, remember, the input is R4, right? The domain's R4. Has dimension of 4. So the range of nullity, you have to sum up to 4. If you don't get 2 elements in the basis of the range, you did something wrong. Let's look at the range. Well, the range is easy. Because the range is the set of all your output vectors. And it's the set of all images. X, Y, Z, and T have to be real numbers because that 4 vector is R4, right? So that is your range, set of all those vectors. If you look at this, what this means play the same game as we did for the kernel. Just list the coefficients for each variable. And remember, range is a subset of the codomain. Codomain is R3, which means our set should be 3 vectors. -1, 0, 1. Should be. Then it was 1, 2, 3. And 1, -1, 3. That set of vectors spans the range of F. But they're clearly not linearly independent. So remember, we had a spanning set. How did we take that spanning set to form a basis? What did we do? So what happens if you remove a vector that's a linear combination of the others from the spanning set? Does your new set still span?
Yeah.
Yes. So remember what we did? We just removed all the vectors that were linear combinations of the others, of the previous ones. How did we do that? How did we determine which ones were linearly independent?
Each column, vector, column, and each fixed separated.
Oh, but wait a minute. Let me just do that. Which 2 vectors do we remove? And let's use a script R to represent basis for the range. There is our basis for the range. And what is the rank then? Right, it's the dimension of the range, which is what? As it should be. You can always, of course, verify that 2 plus 2 equals 4, which is the dimension of R4. So more overreducing. Questions there? Finding range and kernel? Next, let's try it again. This time, we're dealing with the Lorentz operator. R3 to R3. We do the same thing, find basis for the range and kernel, and determine their dimension. All right. I'm not going to go through the step-by-step like I did in the previous one. You should be able to see where that matrix came from, right? So, what is the kernel again? What's the kernel of a transformation? The linear mapping?
Would that just be nullity of,
So that's the dimension of the kernel.
Dimension.
What is the kernel itself?
what is the kernel?
That's 1 to 1.
All the inputs, so L equals 0.
It's the set of all vectors from the domain that map to the 0 vector of the codomain. And so remember, you just set your output equals 0, and solve. Which is why we have this matrix, right? Reduce that. Just make sure that you can get that. How many free variables do we have? One free variable. That means the nullity is going to be 1. So we only have 1 vector in the basis. What is that vector?
So 3, -1, -0.
Why are you giving me a forward vector?
3, -1, 1.
Yep. Remember, your kernel has to be a subset of your domain. And the domains are three. So 3, -1, 1 is the only vector in your basis. This time I'll use the terminology defines. How many vectors should be in a basis for the range? What are they?
The vectors.
Yeah, what are the two vectors?
1, 0, 1, 2, 1.
1, 0, 1, 2, 1, 1. What's the nullity? How do you know it's one? Oh, yeah, but in terms of basis. So in terms of basis, how do you know the nullity is one?
Because nullity is the dimension of the kernel.
And what's the dimension by definition? By definition, right? In this case, it's one, but what's the definition of dimension?
Is it how many columns have three variables?
How many vectors are in that?
Number of vectors in a basis. Well, yes, it is technically the number of free variables, but internal elements are in the basis. So nullity is one. What is the rank?
Two.
Why?
The dimension of the range basis.
Right, so in terms of just strictly basis.
Number of elements.
Yeah, number of elements in the basis for the range. Or how else could you have figured it out?
The number of leading ones.
Okay, that's true. Or,
Like the theorem with the nullity.
right, nullity theorem. The sum has to be the dimension of the domain, right? And the dimension of the domain is 3.
Can you explain how you're getting 1 for row 3 in the kernel?
I got 3 negative. I got negative 3, 1, 0.
So remember what we did before. Yes, that is true, right? The last column is negative 3, 1, 0. Right, that is a system. And they have to solve for the free variable. Or solve in terms of the free variable. So I would say what? X minus 3c is 0, so what is x? 3 times z. Y plus z equals 0, so what is y? Negative z. And z is your free variable, so that last column has to be 1. Or that last row has to be 1. So that's how you get the 3, -1, 1. that make sense? So again, if I go back, I didn't really show it here, except for right here, what I did, right? I just wrote each variable x, y, z, and t in terms of your free variables. In this case, z and t are the free, because it's the comp stub. Right, so the only time you should have a 0 as an entry in your kernel is if you get like 0, 0, 1, 0. Right, then that would mean that this would equal 0 all the time. Were either of those two transformations an isomorphism?
The second one?
Second one's an isomorphism?
Clearly not.
Remember, what is an isomorphism? What does it mean to be an isomorphism? What does it mean for a transformation to be 1-to-1? Be careful. The kernel doesn't equal 0. Remember, the kernel's a set, it can't equal a number. So what about the kernel is 0? Or, I think what you're trying to say is the kernel's only has only the 0 vector in it. What's the dimension of a basis that, or what is the dimension of a vector space whose basis is only the 0 vector? 0. So the dimension of the kernel is 0. Did either of those two have a nullity of 0? So neither of them are 1-to-1, automatically they're not isomorphisms. Are either of them onto? No. What does it mean if a mapping is onto? Of the, which one? There's two. The totally. Oh, but wait a minute. We happen to know where's the rank nullity? Where's the rank nullity here? So two cases. If it's a transformation or an operator, right? Remember, operator is just a transformation where you go from vector space into itself. Deal with the operator. Is it possible for a transfer for an operator, a linear operator, to be 1-to-1 or onto, but not both? No. Do you know why?
I could come up with a counterexample.
It's good enough reason. The rank nullity theorem shows that that can't happen. Nullity plus range has to be the dimension of the domain, which means it has to also be the dimension of the total domain, because it's the same. If it's 1-to-1, nullity is 0. Means your rank has to be 3, automatically makes it onto. If it's onto, I use 3 because of R3. If it's onto, then you know that the rank is the dimension of your codomain, which has to be the dimension of the domain because it's the same vector space. Which means your nullity has to be 0, makes it 1-to-1. If it's just a transformation, can you have a transformation that's 1-to-1 or onto, but not both? Yeah, you can. Remember, to be onto, the rank has to be the dimension of the codomain. Right, if I just go back to here, for instance, R4 and R3, you could conceivably come up with a linear transformation that's not 1-to-1, would have a nullity of 1, or I'm sorry, nullity of 1, and a rank of 3. 1 plus 3 is 4, which is the dimension of the domain, but the dimension of your codomain here is 3. And the rank is 3, thus it'd be onto, but not 1-to-1. And vice versa. Right? You could have a nullity of 0, which means your rank would have to be 4. Which means it's 1-to-1, but not onto. And now we have proof. All right, so we're given a linear mapping from V to W. Oh, I'm sorry, V into U, and the kernel is called, we're just going to call the kernel W. F of V equals U. The coset is V plus W. Defined to be the set of all V plus little w, where little w is in your kernel. I want to show that that is the pre-image of U. So we're going to say that B prime is an element of the pre-image of U. Remember, pre-image is going to be an entire set. It's a set of the inputs. Well, that means by definition that V, or I'm sorry, U, has to be the image of V prime under F. Our goal is to show that V prime has to be the coset. V prime minus V has to be in V. Which means F of V prime minus V has to be F of V prime minus F of V. Oh, wait a minute. F of V prime, didn't we just say that to you? Right, because we're saying that V prime is the pre-image of U. And f of v has to be u. Because that's the definition of f. U minus u is 0. V prime minus v has to be in the kernel, right? Because it maps to your 0 vector. But that means that v prime is in the coset, right? So you can go v plus v prime minus v. Has to be in the coset, right? Because that's the definition of coset, isn't it? Where we said coset was v plus w is the set of all vectors v plus elements of the kernel. That is the definition of subset. To prove that two sets are equal, you have to prove that they're subsets of each other. We just went one direction. Now we have to go the other direction. So what I'm going to do now is say, start with saying that v prime is an element of the coset. Then v prime is v plus some element of the kernel, right? That's the definition of the coset. Right now, f of v prime would have to be f of v plus w, right? We know that v prime is v plus some element of the kernel. By properties of linear transformations, that's f of v plus f of w. But what's f of v? Has to be u by definition. Right? We said that f of v equals u. What's f of w? Where is W located? And what was big W? W is in the kernel, so what's f of W? If W is in the kernel of f, what is f of W?
0.
0. It's just equal to U. F of V prime is U. Which means that V prime is in the pre-image of U. Right? It's a pre-image of U. Sorry, not W. Which means that pre-image of U is a subset of the coset. So look what we just did. We said the wait, sorry, I did that the wrong way, didn't I? I started with V plus W. V plus W is a subset of the pre-image. So we've shown that the pre-image is a subset of the coset. The coset is a subset of the pre-image. Therefore, they're the same. Which is precisely what we wanted. The coset is the pre-image of U. Why is that useful? Who cares? It's math. It's interesting. It's all that matters. Yeah, it's not going to take us 6 minutes to get through. Thank you very much. Any questions on the kernel or the image? Well, this part, coset and pre-image, that's not really useful. In terms of applications, you would never care about. But we're mathematicians, so we do care. But I don't know who created it. Someone came up with the idea of the coset. And said, oh, look, we'll define this as the coset. Look, it's the pre-image.
Every time I hear about math, like some do it's either some do wants to make something easier or some do wants to prove something harder.
Yes. Generally, it's, we know something interesting, so let's prove this. It's a very rare individual. It's a very rare individual who actually creates a branch of math.
Yeah, but one do, you said yourself one do one and so like say
Proof theory.
yeah.
Oh, look, this has no application in physics, and it turns out it actually does.
How long are you gonna take someone to try to get for this? Like this? Yeah.
I'm sure. Sure, some popular idea. I just don't know what it is. So good news and bad news all rolled up into one. No more things. Because your book doesn't really go into it. That is a bad news. You have no way to practice this. Because your book doesn't go into it.
I'm going.
I think the second text might. Right, the supplementary text that I have assigned, that might. So you might be able to find a problem. But in terms of my lab math, there's no. I think there was one problem. Like, there's no point in assigning almost one question mark 1 point. So. So that means, the good news, of course, means you don't have any homework. Bad news means you can't really practice this and see if you're right or wrong. So I would just recommend looking through the practice problems that are assigned on this kind of stuff. And check with the back of the book. We looked at, on Tuesday, determining the matrix of a linear transformation. Right, we define what it is and how to find it. And that would be it on linear transformations. After that, we look at eigenvalues, which is also only 2 days.
I don't think they still are in your book, I just share.
Oh, it is in there, just maybe under the section of linear transformations.
Oh.
They may not have a separate section dedicated to it. I think they put it all together. Because I know there's practice problems on kernel and range. There's just nothing on my lab. Yeah, the first book sucks. It really does. Never using it again. Have a good weekend. The the final project is on eigenvalues and stuff. It's actually using eigenvalues in the Fibonacci sequence. Really interesting. The second project's on the Fibonacci sequence in terms of eigenvalues.
You don't need to sign out, right?
Really cool.
Okay, so.
But that means, of course, I think I have it set to go to become available on Tuesday, because that's when I was going to do eigenvalues. I don't remember if I changed it or not. But that final project won't be due until the end of the semester, May 1st, our last official meeting. And I believe I've already pushed all of the homeworks back. I think I did. I just check the due date and make sure that it does match what I'm going to get in class. It's not going to match on the agenda, because I didn't change any of the agenda due dates, but I did change it in terms of the due date on campus and on my lab. Have a good weekend. I just pushed everything back in class.
Yep.